All right, picture this, a hacker, a locked phone, and time is running out. Their goal? To get inside. But to do that, they have to outsmart the math. So today, we're going to open up that hacker's playbook and really understand the fundamental code they use to beat the odds. So, here's the first hurdle they've got to clear. Seems pretty simple, right? Just a standard 4-digit PIN. Before we go any further, just what's your gut feeling? How many different codes could there actually be?
10,000. Yeah, from 0000 all the way up to 9999. Suddenly, just guessing doesn't sound like a great plan, does it? That's a massive field of possibilities. The hacker needs a strategy. They need a map of this whole digital landscape.
And that right there is our first step. You know, before you can find the needle in the haystack, you've got to get a sense of just how big that haystack is. In the world of probability, that means defining the entire universe of what could happen.
This universe has a name. It's called the sample space. And it sounds kind of technical, but it's a really simple idea. It's just a set of every single possible outcome. For our hacker, the sample space is all 10,000 of those pins. It is the complete map of the problem.
Okay, so you've got this giant map, but the hacker is only looking for one specific spot on it. That's what we call an event. It's the one outcome we actually care about. In this case, it's that one single correct pin that unlocks the phone. And here's where it all clicks together. At its heart, probability is just a simple fraction. It's the number of things you want, that's our event, the one correct pin, divided by everything that could possibly happen, our sample space of 10,000 pins. The odds are, quite literally, 1 in 10,000.
But wait a second. How did we even get to that 10,000 number so fast? I mean, we didn't sit here and write down every number from 1 to 10,000. When the numbers get huge, and trust me, in computer science they get huge, listing them all out is impossible. You need a shortcut. You need a way to count on a massive scale. And this is that beautiful shortcut. It's called the multiplication rule. You just break it down piece by piece. For that first digit, you have 10 options, right? 0 through 9. For the second digit, you've got another 10 options. Same for the third, and same for the fourth. You just multiply them. 10 times 10 times 10 times 10. Boom. There's your 10,000. Now all of this, it's all building up to the single most important question you can ask when you're staring down a problem like this. Seriously, this is the question that separates the beginners from the pros, and it tells you exactly which tool to pull out of your mathematical toolbox.
That's it. That's the whole thing. Does the sequence, the arrangement, the order of the items actually change the result? Your answer to this one question changes absolutely everything about how you solve the problem. And this is the perfect way to think about it. For a PIN code, order is everything. 1, 2, 3, 4 gets you in, 4, 3, 2, 1 gets you locked out. It's critical. But now, think about a fruit basket. If you need an apple and a banana, who cares which one you grabbed first? The end result, the group of fruit in your basket, is exactly the same. So when that order does matter, like with our PIN code, we're dealing with something called a permutation. Think of it as a specific arrangement. Things like passwords, the results of a race, lining people up for a photo, these are all permutations, because if you change the order, you get a completely different outcome.
And on the flip side, when order doesn't matter, like with our fruit basket, we've got a combination. Here, all we care about is the group, which people are on the team, not the order you picked them in, which lottery numbers were drawn, not the sequence they popped out of the machine. It's all about the final selection.
This table just lays it all out perfectly. For permutations, the core idea is arrangement. The keyword is order, and a classic computer science example is scheduling processes. The order they run in is absolutely vital. Then for combinations, the idea is selection, the keyword is choose, and a great example is picking which features to use for a machine learning model. It's the group of features that matters, not the order you happen to select them in.
So why are we getting so deep into this? I mean, why does this matter beyond our hacker trying to unlock a phone? Because this simple idea, permutation versus combination, it's not just some math puzzle. It's the fundamental building block for some of the most powerful tech we use every single day.
I mean, just look at where this stuff shows up. In cryptography, it's how you calculate the time it would take to brute force a password. In algorithm analysis, it helps us figure out how well our code will actually perform. In engineering, it's used to predict when a server might fail. And in AI, it is the bedrock of models that do things like filter spam out of your email. It all comes back to counting the possibilities correctly. So as we wrap this up, I want to leave you with the one key piece of code, the one line of thinking that you should absolutely take away from all of this. It's this, right here.
No matter what you're working on, always stop and ask that one simple, powerful question. Does order matter? Answering that correctly isn't just one of the steps, it's the key that unlocks the entire problem.
So there you have it. You've now got the key to the hacker's playbook. You get the difference between an arrangement and a selection. You have the fundamental question you need to ask. The only question left is, what problem are you going to solve next?